Okay, Aubrey, we're going to do like the first two examples of 2-6. We're not going to do a whole lot today because 2-6 is not a very long section anyway. Like it's only like 2 pages and half of them are graphs. But I did accidentally cut off example 2, so I'll have you write that down here after bit. Yeah, because we have example 1 and example 3, but we don't have example 2. The first thing it talks about, though, is continuous functions. Yeah, continuous. Okay, continuous means like it's not got any holes or breaks or jumps. Okay, so 3 things that can make him not continuous is a hole in the function, like you see here, right? There's a hole right there. Or it could have a vertical asymptote. Do we know what a vertical asymptote looks like? Do you know what I'm talking about when I talk about vertical asymptote?
Is that the...
Like the dotted line, right? Like one of these guys, this guy, that vertical asymptote where he doesn't touch. Yeah, that could be a problem that makes him not continuous. And then we could have a break in the graph, okay? And breaks usually happen when you have a piecewise function. Like, let's say, I don't know, let's say like I have this, right? That's a break in a graph, right, for a piecewise function, okay? Otherwise, if it doesn't have any of those 3 things, then it's going to be a continuous function. So, I don't know why I was teaching calculus like last year, I'm pretty sure, and they had the hardest time like figuring out whether it was continuous or not. I'm like, that's not really that hard of a concept, but whatever. So, this is how I explain to them, right? If you drive your car on the line of here, like let's say I'm going with my car, and I don't hit a pothole, and I don't drop my car off a dead end, and he can continue on forever, and I don't have any issues, then it is a continuous function on all rails. So this function describe the intervals of continuity. He is continuous from negative infinity to positive infinity. There are no problems here. Right? Like he's going to go on forever. I'm not going to hit a pothole. Like I'm going to poop my pants when I go down the hill, but like it's going to be fine. Right? Versus this guy, he has a pothole that he's going to run into at 3. We don't care that the y coordinate is 1. We only care about the x coordinate. So he is continuous from negative infinity until we get to 3, and then from 3 to infinity. Okay, another way of writing that is all reals except 3. Except x equals 3. So however you want to write that, that's totally fine. Either way, those mean the same thing. It just says we have a pothole at 3, we're going to have a problem. Right? Okay? So it's just where he's continuous, where he's not continuous. If there's a break, if there's a vertical asymptote, if there's a hole, that's where he's not going to be continuous. I know. I'll have you write an example 2. I have them. I don't know where we're going to write him, but anyway. Okay, let's go through these. They have identity function. This is a linear function. I don't know why I included these in here because you guys know what these are. Y equals x is this function right here, is a linear function. They call the next one the squaring function. Y equals x squared. They call that the squaring function. What do we call it?
Which one?
Y equals x squared. Yeah. The squaring function. Quadratic, right. I don't know. It's just weird. This book must be old that they call it that. Okay, they call the next one the cubing function, y equals x cubed, and y equals x cubed looks like this. Sometimes he could be humpier, like he could look like this instead, right? And have like really big humps in the middle. Whatever. What do we call it? Cubic, right? We don't call it the cubing function. We call it cubic. Whatever.
That's the third one?
That's the third one. Okay, this one we do call the square root function. He looks like y equals square root of x. And he starts in the middle, goes on forever. He doesn't go forever to the left because can't take the square root of a negative, right?
Can you go out a little bit?
Yeah, I'm just like rewriting these. You don't have to rewrite any of these, but
What's the column say? Linear.
linear quadratic. Okay. They have a cubic root function, which we call a cube root function. Y equals the cubic root of x, and he does like this little bit, but then he goes back forever the other direction because you can take the cubic root of a negative. Whatever. Absolute value function, y equals the absolute value of x. He looks like a V. We know that, right? Hopefully, maybe. He's at a 45-degree angle unless we like put some numbers in there, and then we could like flatten him out or make him taller. Y equals absolute. It's right here, but I just switched it to Y. Whatever. Okay, and then we have example 2. Okay, here you go. This is what you're gonna have to write. Sorry, these didn't include in here. So here's the first part A of example 2. We'll do example 2 and then we'll stop. Graph each function. I know we just got done graphing piecewise functions, but I think it was for trig, not for college algebra. So I don't think we've done this before yet. Piecewise function. Piecewise. These are all piecewise functions, if you want to write that in there. Piecewise. Piecewise.
Where's my right?
Piecewise.
How much
Piecewise.
room is this?
It's gonna take a little bit of room, honestly. So you could put them down here at the very bottom if you want to.
Okay.
Because we're gonna have to graph these, and that takes a little bit of room. So I'm gonna put my graphs over here and over here, because we don't need that room. So stuff at the top, graphs on the side, whatever. That's what he is. Sorry he didn't get included. I don't know why. Sometimes when I put these over, Macy said it should work now.
Okay.
Aiden, I sent that to you too. If you want to put whatever on there. All of the mama basketball ones or whatever, and then like if they're going through this book and they take an order, like you get everything from that. Like if they order a shirt with that on it, whatever, then all that money goes to you, besides the transfer and the shirt and stuff, whatever. So more to keep track of when we get back. Yay! So anyway, okay, do we get A written down? All right, here's the deal. When we have a piecewise function, it's exactly the way that it sounds. We have 2 pieces, okay? You can have a piecewise function with 3 pieces or 4 pieces or a ton of pieces, right? You can have tons of pieces for your piecewise function, okay? All right, and basically it's 2 graphs all in one, okay? And the place where those 2 graphs cut off is right here. This is called the domain, okay? And so the graph like basically splits in half at an x coordinate of 2, all right? So what's happening here is if I graph this function, I'm thinking x coordinate of 2 is like 1, 2, like right here, okay? Draw that line really lightly, by the way, because we're going to erase him. That's where my graph splits in half, okay? So something's going on this side and something else is going on this side, okay? He splits in half at that value of 2. If you draw this line, draw him very lightly, okay, because we're going to move him around. All right, next, this guy is what we're going to graph when he is less than or equal to 2. So on this side of the graph, we're going to graph this function, okay? Just think of that as like y equals negative 2x plus 5, right? So y equals negative 2x plus 5 lives over here. How do I graph that? What kind of function is that? A linear, right? Okay. We're only drawing it up to this guy, right? So I want to make sure I only put him from here going that way. Only on the left side. Only to the left side of that line is where I'm going to draw him. Now, we need to decide. Am I going too
Is
fast?
this like the shading thing?
No, this is not shading at all. That's when you have less than or equal to stuff, okay? Which I guess we have less than or equal to stuff here, but that's different, okay? So this guy right here, this dot, where he's touching that line at 2, I need to figure out whether he's a solid dot or an open dot, okay? So look over here. Look at the difference between these two. This function is the one I graphed. Is he going to be a solid dot or an open dot? Solid, right? Okay? When I go to graph this one, he's going to be an open dot on that line, right? Okay? So on this half of the function, I'm graphing y equals x plus 1. Y equals x plus 1, okay? All right, so to do that, I'm going to start at 1, and I'm going to go up 1 over 1, 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 right? Okay, and I draw my line. Except, I only want him to be on the right side of that line, right? So I'm only going to graph him there to there, right? Because he splits in half right here. Whoop. So he's the blue function on the left side, he's the pink function on the other side. The only thing that I have to fix is I need to erase my middle line, by the way. He's gone now, right? And what else? Yeah, the pink one needs to be an open circle right here. So he's not touching there. Got it?
Thanks.
Not touching. Not touching. Not touching. Okay, happy with that? That's how you do that. Piecewise function, just graphing two functions, but like you're separated into two pieces. Got it? Or sometimes three pieces. Okay?
And how do you know which array, like the line is even?
Where it separates right here. The domain, that right side guy tells you where he's like cut off at. Right? That's like your cut mark. We're gonna graph another one here in a second. Okay? Okay, are we good on that one? Example 2, part A? Okay? All right. Part B is this guy right here. So I'm gonna put him over here on this side. Okay, it's just another one to practice. Whatever.
So then the line would just be the mid.
Yeah. Okay. Before we graph this thing, I know your homework assignment asks you to do this. If you're given this piecewise function, how do I find f of negative 2?
You just plug it in.
You plug it in. Which one?
The one, the top one.
I'm only plugging in these numbers if x is less than or equal to 0 or if x is greater than 0. Okay? So if I'm plugging in negative 2, is that less than or equal to 0 or greater than 0?
Less than 0.
Less than or equal to 0. So I'm going to plug it into this equation, right? So 2 times negative 2 plus 3 is negative 1. Okay, so f of negative 2 is negative 1. What if they say f of 0? Where does he go?
The same one.
The same one because it's equal to 0 there, right? Okay, so we have to pay attention to the equal sign. So I'm going to plug 0 into this top equation again. 2 times 0 plus 3, which is just 3. Okay, I just made these numbers up, by the way. F of 2 is going to go in the bottom equation because that 2 is greater than 0, so he's going to go down here, and I'm going to plug 2 in there. Negative 2 squared plus 3. Be careful, this negative was already there, so we're not squaring the negative as well. What does this come out to be? Negative 2 squared. What? Negative 4, yeah. Right, because the negative's on the outside. Negative 4 plus 3 is negative 1, so that's what that is, right? So if they ask you to plug points in, you're not plugging into both equations, you're only plugging into the one that you need, right? Yeah. Okay, all right, now let's graph the dang thing. Okay, all right, here we go. All right, in my section where he switches, where does he switch from one function to the other one?
The middle one.
At the middle line at 0, right here, right? I'm going to make him a solid line, okay? So at this red line right here, which I'm going to erase, right? I'm just putting that there for my mental note, okay? On the left side, he is going to be graphed as y equals 2x plus 3, right? On the right side, he's going to be graphed as negative x squared plus 3, okay?
How do you know which one goes on which side?
Because of this right here. If x is less than 0, less than means the left side, he's going to be that function. If x is greater than 0, this guy, good question, right side. Got it? Make sense? Okay. Usually they'll put the top one as the left and the right because you're going left to right. Okay, so that's how that works. Okay, so on the left side we have what kind of function? Linear, right? 2x plus 3, right, on the left side. Okay, so we're going to start at 3. 1, 2, 3, okay? And I'm going to put a dot, and I'm going to go up 2 and over 1, right, because that's my slope. And up 2 and over 1, or I'm going to go down 2 to the left 1, and down 2 to the left 1, right? I start at 3 and go up 2 over 1, up 2 over 1. Okay, so there's my dots, and before I connect the dots, I only want to graph him on the left side of the line, so I'm only going to do this side. Boop. And he goes forever that direction. And I'm going to erase this dot right here. Okay? Now, should he be an open circle or closed circle on that line?
Close.
Yeah. If x is less than or equal to 0, that means a closed circle right there. Yeah. Okay. All right. Good? Are we doing okay so far? Are we stuck at all? On the right side, negative x squared plus 3. What does that thing look like? He's a quadratic function. He's a parabola, right? And he's facing down, right? He's like a frowny face. But what's the 3 do? Moves him up 3. So he looks like this. Whoop, like that, right? But we only want to graph him on the right side. Okay? And where he touches that middle line, is he an open circle or closed circle? right? He's open, right? Over there, okay? So this is kind of weird because we have an open circle over top of a closed circle. So technically this guy is filled in, right?
So all.
Okay? So if we're talking about this thing, if he's continuous, even though he's two pieces, he will be continuous, right? Like I'm going to start my car and travel along because he's filled in from the top equation, right? I'll be able to travel all along that line and be fine, right? So he is continuous. It doesn't ask me to do that, but he's continuous on all rails or from negative infinity to positive infinity, right? How about this one? Is he continuous? No. What do I put for his continuity?
All rails except for 2.
All rails except for 2. Right? Because he's going to drop off at 2. Okay? Good? Questions about that? Piecewise functions. Weird. Yeah. Weird. Yeah. In like story problems, a scenario of when you would do a piecewise function is like, let's say you're at an amusement park, right? And let's say the amount of money you pay for an amusement park is your age. So if you're 1 year old, you pay $1 to get in. If you're 2 years old, you pay $2 to get in. At 3 years old, you pay $3 to get in. Does that mean if you're 60 years old, you pay $60 to get in? Probably. So what I'm going to do is you pay your age, right? So 1 year old pays $1, 2 years old pays $2, whatever. Except it caps out at $30, right? So if you're over 30 years old, you're maxed out at $30. So it's going to do this, right? So what that's going to look like is you pay your age, right? So if you are younger than 30 years old, you are going to pay your age. So if I'm 26, I'm going to plug 26 in here and I'm going to pay 26, right? If I'm 12, I'm going to pay 12, right? But if you are greater than or equal to 30, you are only going to pay $30. That's why this line's a flat line, because this is like y equals 30 right here, and this is y equals x right here, right? And the line right here where it switches would be at 30, right? Okay, that's not drawn to scale, but whatever. Does that make sense? Yeah. So that's an example of kind of how this works, right? Okay, and in that case, that would be a continuous function, right? It would have to be continuous, because if we had a hole in the graph, like we would have somebody not knowing how much they pay, right? Right.
They'd be free.
They'd be free, sure. Yeah. Okay, good. All right, I'll go run off your homework summit. Bye, Aubrey.